Hello, I'm Eric, here to tell you about Ray data streaming. So this talk will be a bit more of a deep dive into this streaming feature of Ray data. Some of you might have seen Stephanie and Scott's talk yesterday about how to streaming and its performance for training. Here I'm going to talk both about ML inference and training, the streaming feature, and kind of dive into kind of all the code examples of how it works, how to debug this thing. And I'm also going to talk a bit about the backend, how this works in Ray core. So about me, I'm the tech lead for Ray at Anyscale. My focus these days is a lot on Ray data and also Ray core. So a bit about ML workloads and data. Clearly data is kind of ubiquitous across ML workloads. But the way I like to think about it is for like the ML lifecycle, there are kind of three steps. There's the ETL phase, and then preprocessing and training. And this is how you get your data to your ML workflows. And concretely, the ETL step involves things like ingesting the data at your company, joining data tables, and so on. Preprocessing involves preparing your data for training, which it might involve resizing images, video decoding, data augmentation, things like that. And then finally, you have to do your actual training, which might involve leveraging your favorite ML framework like PyTorch, LLMs, and so on. Right? Kind of in very general terms, the first two steps are typically run on a lot of CPUs. They might be CPU intensive. And the latter step is often running on GPUs. And when you think about the ML team or ML organization, the latter two steps are what we care about most of the times. In the first step might be a different org, like a data team or something like that. So we're going to focus on kind of challenges in the area and how to solve them. And kind of in a nutshell, like from kind of the Ray perspective, the challenges we see here are infra silos and fragmentation. So there are many different systems being used for this, different clusters for preprocessing training, different systems for inference versus training. And this leads to a lot of overheads. So there are performance overheads, moving data between systems, between different clusters, and operational overheads, like the development lifecycle can be much more, annoying. You have to work with a lot of different technologies. So our kind of vision for simplifying this with Ray is to kind of simplify those latter two steps. So for ETL, this is not something we're really focusing on with Ray because there's already a mature ecosystem of solutions out there, data warehouses, Spark, so on. But we kind of see pain points with Ray, where we're trying to simplify, where preprocessing and training can be just done very simply in one Python script, no matter the complexity of your workload. And early users of Ray data are kind of echoing kind of this vision, like they're seeing like improvements in iteration speed and performance using Ray data for training. So what is Ray data? Ray data is one of several Ray libraries alongside train, tune, serve, and rlib. And all these libraries are kind of built on Ray core. And Ray core provides tasks, actors, and objects that do all the distributed heavy lifting for these libraries. Ray data is a relatively new library in the Ray ecosystem. So when Ray was first created, there was just the low-level APIs. We started with a couple initial libraries for reinforcement learning, hyperparameter tuning. And it's only kind of relatively recently we tried to complete the entire ML lifecycle with the data trained libraries and so on. If you look at the tech-wise, Ray data is unsurprisingly a distributed data set. So that means it has to distribute its data across the clusters. So you can kind of think about a Ray data set as a number of blocks spread across the cluster, and every block is represented as a Ray object. So in this way, Ray data can scale to ingesting or processing data across a system. And Ray data is using Apache Arrow as a standard under the hood. So it lets it interoperate with many other systems. For example, it can very easily ingest data from S3, Spark, and so on using kind of Arrow's I/O APIs. And it can also efficiently send data to other systems like TensorFlow, PyTorch, and so on. The Ray data APIs that you kind of need to know for this talk are those for I/O, for transformation, and consuming data. So this is probably not unfamiliar if you're used to working with dataset APIs. We have APIs like read Parquet, read CSV. You can transform your data with a UDF that you put in. And you can also consume data. So one thing I do want to point out is Ray data is a little bit different from other dataset APIs in that its iteration API is designed for high performance. So you can iterate over batches in Ray data at multiple gigabytes a second, which is not the typical design point. And the reason for this is RAID data is designed to be used for distributed training, where you want to feed data into your GPUs at high throughput. OK, so what's this streaming feature I'm talking about? So previous versions of RAID data, basically last year, used a kind of bulk execution strategy. So this is a very simple, naive execution strategy of when you try to execute a data job, you're loading all the data into memory, then apply any transformations onto it, and then send it to the destination. So this works very simply, but there's some limitations. For example, if you're trying to load data that's much bigger than your cluster memory, you have to spill the disk, and this is often introduces a lot of performance overheads. Not to mention, if your data set is just bigger than your cluster disk, your job cannot complete at all. So in the new kind of streaming execution paradigm, the API doesn't really change, but under the hood, RAID data is instead creating a series of operators for your RAID data job and stream the data from the data source through those operators and kind of to your final data sink without needing to spill the disk. So why did we do this? So there are some obvious benefits, but I like to think about it like this kind of 2x2 matrix. So there are two kind of workloads that we address with RAID data. First thing, I think of CPU-only pipelines. Like say you just want to apply a UDF and then consume your result. It's a pretty straightforward pipeline. And then we have heterogeneous pipelines, where some stages of your pipelines might run on CPUs and some might run on GPUs. So the kind of pros and cons of streaming and bulk are different across these workloads. So let's look at the very simple workload first. And let me walk you through an example. So a very simple CPU-only pipeline might look like this. And here I'm using a batch inference as an example. You might want to read data, preprocess data, do inference, and then save your data. And in code, it would look something like this. So you define your model and preprocessing function and some inference function. And here I'm going to flesh this one out. In Ray, these kind of UDFs take dig some numpy arrays and produce dig some numpy arrays. So all this function is doing is calling a model and returning the outputs. And I can build my data pipeline. So I could use Ray data read parquet to load the data. I use a map transformation with that preprocessing function, and then do that inference function before saving my data. So the way this pipeline executes is as a single stage. So this means that all these functions can run on CPUs. Therefore, they can be executed kind of in one CPU task. You think about it, just one thing for RAID to run. And when you execute it in a bulk way, it's very straightforward. So in this example, say you have 3 input partitions. We have our stage. We just compute all of them and then get all the outputs all at once. And you can't get any output until everything's done. So what are the pros and cons of this? One kind of not obvious thing is actually this is memory optimal. So there's no advantage of streaming in this situation for memory usage. That's because there's no multiple stages to stream data through. There's just one stage. As soon as the data goes in, it's done. There's no intermediate data. So this is actually pretty great for inference, and that's why Spark is great for inference in these settings as well. What it's not good for is distributed training, because when you're trying to consume like a terabyte data set, you don't want to process a terabyte data before you start your PyTorch job. You want to process data as soon as possible. Now streaming solves this problem, because with streaming, you create that operator, and for each data partition, you can send it to the operator, and as soon as that operator is finished computed data, you can send it to your downstream sink, and so on and so forth in an incremental way. So that solves our problem for distributed training. So the streaming model is kind of better in this case. So you see, for these simple pipelines, the main benefit of streaming is for distributed training. Now for heterogeneous pipelines, there are more benefits. So here's an example of a heterogeneous pipeline where I have that read, preprocess, inference, save kind of job, but one change. The inference is running on a GPU. I might have a GPU model. And in Ray, in code, this might look something like this. For GPU-powered UDFs, typically you write a class instead of a function. And in the constructor of the function, you can set up your model that loads it into, initializes the GPU, loads the model into GPU memory. And then you have a call function to process a batch of data with that initialized model. And the pipeline is a little bit modified. For that GPU stage, we map batches that class. We can tell Ray to use 1 GPU per actor to run these transformations. And then we can tell Ray how many actors to use to execute that operator. If you look at the physical execution for this, now there's multiple stages or multiple operators to run. You have your CPU preprocessing stage, you have your GPU inference stage, and you have a final CPU saving stage. And why are these separate stages? It's because you might want to scale them independently. Say you have a lot of CPU machines, you want those to run tasks from stage 1, then runs tasks from stage 2 on the GPU machines, and you can run stage 3 on the CPU machines again. So if you look at the bulk execution plan for this is where you start running into problems. If you run stage 1, you have to put the output data for this somewhere, probably into disk or materialized into storage. And then if you want stage 2, read that data back again, and then stage 3, you read the data. So this introduces a lot of blocking calls. You can't fully utilize the resources in your cluster and for these type of pipelines. So we see kind of for these types of pipelines, a bulk execution is really not great. And streaming is actually does solve this problem, because for every operator, you can run that data, send it to the next operator, and then start processing data for the next partition and so on. And so you see here, we never have to materialize the intermediate data in bulk and spill it to disk. So we can avoid that overhead. Yeah. So kind of in summary, there are some advantages of streaming execution, even for simple CPU-only pipelines, but it really shines for heterogeneous use cases. Another interesting comparison is how does streaming compare to other streaming data loaders out there? Like you might be familiar with PyTorch data or TF data. There are many of these things out there. So one way of looking at this is along these dimensions. So multi-processing-based data loaders can support some of these functions that usually have some sort of caching and fault tolerance, but are a little bit more limited for things like partitioning data across the cluster or supporting heterogeneous clusters or anything that involves nodes of the cluster working together. Now, TF data is kind of an interesting system. It's a little bit more general than the other data loaders. TF data is actually a fully distributed system. It supports automatic data partitioning and caching. If any of you were at the Netflix talk yesterday, you see also how they combine it with Ray and also support heterogeneous clusters, which is something also Ray data supports natively, along with supporting inference pipelines. OK, so next I want to walk through an end-to-end code example for these pipelines. So let's look at a video inference pipeline. So in this example, we have 4 logical steps. You have a bunch of video files to start with. The first step is you would decode the video into frames. You want to apply one model to annotate the frames, the second model to classify the frames, and then you're writing the output. So we have to write kind of functions for all these stages. And here's another those familiar UDFs that takes in a numpy dict and returns another numpy dict. So that I can define something like this for decode. For frame annotation, suppose I have a model I want to use to annotate my frames. I can define that model here. For classification, I can have another model. And then for the final step, I don't need any custom code for that. So in code, it will look something like this. I'll highlight some Ray features. So first, you can read video binary files. So Ray provides that kind of read binary files API to read files from disk. If I want to decode frames from that file, I can use a map batches function for my decoder UDF. Ray has this interesting feature where you can customize the resource request per stage. For example, suppose my decoder was a multi-threaded video decoder already. I can tell Ray, I don't want you to over-parallelize this. I want you to allocate 4 CPUs in that machine per task. That way I can support multi-threaded computations. Then I can run the model using a map transformation here with an actor pool of size 5. And then I can run the classification step with a different strategy if I want. For example, I can set GPU 1. I can set the batch size here, so tell Ray, hey, make sure to batch the data into chunks of 64 for this GPU. And I can say, oh, here I just want to use two GPUs for this step. And I can save the output. So this is kind of the most general case of running Ray data streaming with multiple operators. So every operator is running on a different type of resource, like CPU tasks, CPU actors, and GPU actors as well. And what do you get if you actually try to run this script? If you run that script I kind of overviewed before, you'll see that Ray data will print out the operators it creates. And you can kind of see like what they're running on. You can see some are running on a task pool, some are running an actor pool, and the final step is running on a task pool. And Ray data will also provide a kind of a nice progress bar. I think some interesting things to note here from the kind of debugging standpoint is it prints out the CPU resources being used, the GPU resources, and memory, right? So you can see here that it's only using 25 CPUs in the cluster. It's using all the GPUs, and it's using all the memory given to this job. You might be wondering why it's not using all the CPUs. It's because this pipeline happens to be memory limited. So in order to stream the data through the cluster, we only need 25 CPUs. If we use more CPUs than that, we might create too many intermediate objects and start spilling to disk. So that's what this is showing. And the job will eventually finish. And you can kind of diagnose the stuff using the Ray dashboard. So the Ray dashboard has some nice metric views for this. So this is just showing Ray's breakdown of tasks in a cluster by name. If you haven't seen this, it's pretty useful. So you can have a time series view of what actor tasks or what normal tasks are running. And so here you can see it seems like most of the tasks, the active tasks in the pipeline are my frame classification tasks, those orange tasks, and a few were frame annotation tasks, and it seems like the rest of the tasks weren't actually using that much time in my cluster. You can also look at the state of actors. So here, I guess there were, I think, 7 actors and maybe 1 utility actor. You can see that for the entire job run, these actors were kept 100% busy, so they weren't stalled on anything. You can also check physical usage, of course, like network utilization. So you can see here, this pipeline was pushing about 2 gigabytes per second, I guess, of network usage. So that was an inference pipeline. For distributed training, the story is not that much different, actually. So because Ray data is kind of fully general, you can use those inference pipelines for training very well. The main difference is that for inference, you output to a data sink at the very end. But for training, you instead want to split your data into multiple substreams, and each of those substreams you can send to a worker, for example, a PyTorch worker. And in that worker code, you can use an iterator API to kind of pull batches from the stream. There are kind of many interesting advantages using streaming for training. One very common use case is to accelerate the read or preprocessing operation. For example, if your training is actually bottlenecked by reading I/O from S3 or preprocessing your data. So just a very simple benchmark I put together here of this. I think I set up a PyTorch training cluster with 10 G4DN nodes, so I think one GPU each. And I first tried running the job with just those GPU nodes. And it turns out in this case that I was only able to ingest about 1 gigabyte per second because of the limited network and CPU resource on those GPU nodes. And these are very expensive GPU nodes. But by adding just a few relatively cheap CPU nodes, I was able to greatly increase my ingest throughput and hence my GPU utilization, making this much more cost effective. Similarly, for training, you can monitor the GPU utilization, things like that in the training dashboard, storage bandwidth, and also the memory usage of your training jobs. So finally, I want to talk about how data streaming works using Ray. So at a very high level, array data streaming works by implementing the transformations in that data API as operators. And the execution of these operators is actually pretty straightforwardly decomposes into array core primitives. For example, if you're using the default execution strategy for an operator, it's just going to use array task to execute that. Your UEFs for transformations. If you specify an actor pool, of course, it's going to use array actors to run your code. So intermediate data between these kind of stages, between these tasks and actors, are data blocks in the array object store. And the memory usage of these operators is limited, also known as back pressure, to kind of enable efficient streaming without spilling to disk. So this part is interesting because if you think about not having back pressure, what happens is the streaming actually just degrades to bulk execution. So basically, the back pressure is the main difference between streaming and bulk. So just an example of how array data schedules the execution of each stage under the hood. Let's look at an example of that 4-stage pipeline and look at a snapshot of what's happening in the cluster at this point in time. So I have those 4 operators, and here I'm showing logically those colored diagrams, those colored blocks are the intermediate data produced by one operator to be consumed by the next operator. So those, for example, those purple blocks are produced by decode frames. They're about to be consumed by frame annotations. Okay. So as the job runs, you have these queues between the operators of various sizes. And array data needs to decide, like, what am I going to do to schedule the next unit of work given the current state? Well, looking at this pipeline, you can see that the queue between the decode and frame annotation is the largest. So this is probably telling you something that the decode frames operator is probably producing output faster than the downstream pipeline can consume. So the right action for array data is to throttle this operator, which means reducing the number of active tasks running here. If we look at the next operator, however, its output queue looks pretty small relative to the rest. So in this case, we might actually want to increase the parallelism of this annotation thing. If it was on a task operator, maybe we increase the number of tasks. If it was an actor, if it was an actor pool, we'd try to increase the number of actors up to the size allowed. And for some operators, maybe we just keep the same parallelism. So building an array core is pretty interesting. So a lot of the advantages of array data just come purely from being built on array core. For example, the support for heterogeneous clusters and fault tolerance. We can kind of leverage a lot of features of array just for free. For example, the lineage-based reconstruction of array tasks and actors when a node fails kind of just works for array data. We didn't really have to do anything special for that. And kind of the object store allows many features such as caching and object locality that array data does not really need to kind of re-implement. The final point I want to make is that array core also lets array data scale very well. So when we ran a scale test of how much data we could push just using the array data plane, we were able to push more than a terabyte a second. So you can see that this doesn't really, this lets array data scale very well, and we don't think this will be a bottleneck. So just to summarize, array data streaming scales batch inference and training workloads. It's a much more efficient computational model than the bulk processing back in the past. And the API doesn't really change, the same simple API. So if you're interested in using array data for streaming or inference, our documentation is available at docs.array.io. There's also integration with the array train library and starting with 2.6. So you don't need to, so you can use a train API and pass the data sets to it, and they will be streamed. So what the data team is currently working on is kind of hardening streaming to work robustly in many edge cases. For example, very large clusters or many millions of files, and there are many challenges there. So if you have use cases there, we'd be interested in talking to you. Okay, thank you. Questions? Great question. So the question was, If we want to read from a Kafka queue or something like that, like a true stream source, do we support that? So right now, we do not support reading from kind of unbounded input sources, only like bounded input sources such as like S3 bucket or things like that. But that's the feature that's been asked for, and we might add that in the future. No.
How does we compare with the Spark? Like we talk about RDBs, the level that we get with Spark with the data frame. Can you talk about more explain?
Yeah, a great question. So the question was, how does this compare to Spark RDDs? So I think one slide that's useful is this one. Actually, so RAID data bulk execution was almost exactly the same as RDDs with the same kind of pros and cons. So I would think of RDDs as bulk executed data sets, and then RAID data, the new version of RAID data implements streaming and pipeline execution for data sets. Yeah. Sorry, could you repeat the question? There's some clapping.
After the first epoch, like let's say I'm training book in the shuffle, like what's the guarantee shuffle? Is guarantee shuffle or like once you've got the data set after the first epoch, you keep it on the board or like you go to the
Got it. So the question was, how do we handle shuffling data between epochs? So yeah, that's a good question. So there are a couple strategies. First, we support like TF data and systems like other that. We support a local shuffle. So you can specify like a shuffle window. Like say I want to shuffle a window of 100,000 records to mix records in. We support that. With RAID data, you can also do a true global shuffle of the data using a kind of .random shuffle operation, though this is pretty expensive. We also have something where you can shuffle just the files. So you can, for every epoch, you can randomize the order of files that you read, which some users have found to be the kind of best trade-off. Yeah.
How does the parallelism change? Is it like a real time, or is it set once and then you don't change? If it changes like multiple times, then how do you guarantee the skewness among your key distribution among those tasks?
Yeah, a great question. So the question was, does the parallelism for each operator, is it fixed, or can it dynamically change over time, and does that cause any problems with data skew? It is fully dynamic. So for example, for stages that run on tasks, we can run any number of tasks from 0 to the full cluster parallelism. And for actors, we kind of constrain it to your specification. So if you say use exactly 5 actors, we'll use exactly 5 actors. But if you say let this auto scale between like 2 and 10, we can do that. And as for how it impacts the data skew, we can dynamically adjust that. Because we're just doing data loading, typically we don't have problems about like one key getting too big because there's no like group by operations or anything like that. Yeah.
Sampling as a first order limited, like say I have 2 data sets of 60% from here, 40% in loading.
Yeah, good question. Whether we support sampling, we do have a random sample operator. I don't believe it lets you. It might allow you to combine the 2 data sets, but I'm not sure if it can do that in a fully streaming way. I have to get back to you on that one. Yeah, but you could check out like the random sample function.
When you say streaming, is there any ordering guarantee?
Great. So the question is there any ordering guarantee for streaming? So by default, no. We have a deterministic execution mode that can guarantee order. That you can enable that mode.
Can you chain or unchain operators?
So is the question, can you chain any operators?
Yes, like 2 operators together, so you know like you can avoid it.
Oh yes. You can chain any number of operators in RAID data, and we'll fuse together operators that require the same resources. For example, they both use CPUs. They can get fused together into one task. Well, thanks again.